Alright, in this video, we consider a sequence of functions defined on some interval I. So that is f1 of x, this is a function on this interval. Another function, f2, f3, and so on. And how, if it converges to some function, then in what sense does this sequence converges to this function? So let's begin. There are, in fact, a few different ways to define convergence for a sequence of functions. And the first one we introduce here is pointwise convergence. So that is, if we have a sequence of functions such as this one, and let's pick one point from this interval I. Okay, A is an interval, A is a point in this interval. Then at this point, we can define a sequence of real numbers. Okay, so fn of A. So f1 of A is a real number, f2 of A is a real number, and so on. By the way, the original sequence, this is a sequence of functions, so x is a variable, so it's not determined yet. So this is a function, this is a function, this is a function, but here, this is a number, and so on. So since this is just a sequence of numbers, we can define the convergence, if it converges, to some number that we define as f of A. Okay, so for each point in the interval I, if this sequence converges to some value which we define as f of A, then we say this sequence of functions converges pointwise to this function f of x. Okay, so pointwise convergence. So let's repeat. So we pick each point in the interval one by one, then study the convergence. Okay, so that means in a logical form, we can write this situation as this. For all point A in the interval, so this sequence converges to this. So that means for all epsilon that is positive, there exists a natural number, n, capital N, such that for all natural number, lowercase n, if n lowercase n is greater than or equal to the uppercase n, then the difference between f of A and fn of A is less than epsilon. So first we fix the value of A. Then we just consider the normal sequence of, ordinary sequence of numbers. So in this sense, if this convergence is true for each point in the interval, then we say this is pointwise convergence of this sequence of functions. So what's important here is that since we first fix the value of A, this value of n may depend on the value of A. So maybe we should write this n as n of A because it's dependent on this A. So that means, suppose we have a function like this. So we have a sequence of functions, so that there's lots of functions. And at each point, A, let's say, these numbers may converge to some number, okay? So let's write this as this. And at another point, these values may converge to another value. So by connecting this, we have a function, okay, something like this maybe. So that is f of x, okay? But for each point, how many n's terms we need to ignore before this is achieved. So it may depend on where we are here. So this may depend on this value of a. So in this case, it's pointwise convergence. And in the case of pointwise convergence, we simply write like this. And going to infinity, fn of x converges to f of x. On the other hand, we have another definition of convergence of a sequence of functions, that is uniform convergence. So maybe we should just write a logical form to contrast the difference between the two definitions. That is uniform convergence. So that is for all epsilon that is positive, there exists a natural number, capital N, such that for all a in the interval and for all natural number lowercase n, if lowercase n is greater than or equal to the uppercase n, then the difference between f of a and fn of a is less than epsilon. Okay, so what's the difference? The difference is where we put this for all a. Okay, in this case, this clause is inside, so it comes after there exists n. Okay, so this is before it was in the beginning. Now it's after n. Okay, so that's the difference. So what this means is that in this uniform convergence, this n does not depend on the value of a. So for every a, we have the same value of capital N. So that if we ignore this many terms in the sequence, we always achieve this. So wherever we are in the interval. That's why we call it uniform convergence, because it doesn't depend on where you are. In the case of uniform convergence, we don't write like this because this means pointwise convergence, and it's using the same expression for different meanings is confusing. So sometimes we use something like this: uniform limit, and going to infinity, fn of x is equal to f of x. So uniform convergence, maybe we may put parentheses or maybe just a dash between them or whatever is convenient. And sometimes also use this. So in case of pointwise convergence, we may write this, pointwise. And in case of uniform convergence, we sometimes write like this, two arrows. So this is uniform convergence. So why do we bother with the difference between pointwise convergence and uniform convergence? That's because there can be a great difference in the behavior of the limiting functions, whether it's pointwise convergence or uniform convergence. And here's a theorem that demonstrates the importance of uniform convergence. Okay, suppose we have a sequence of functions on an interval I, uniformly converging converges to a function f of x. So suppose. Then if each fn is continuous on I, then the limiting function f of x is also continuous. on I. Actually, we have already essentially proved this theorem in a previous video about the calculus of power series. So please refer to that video for the hint of the proof. So we'll skip it here. But basically what we can, the basic idea is that if each of fn is continuous, then we can make like this, and since fn converges uniformly to f of x, we can make fn f of x minus fn of x less than some arbitrarily small number, epsilon over 3, and same for any point in any point A in the interval. So from this, we can easily show that f of x, so wait a minute, so this comes from the continuity of each of these functions, right? And this comes from uniform convergence. So from this, we can show that the difference between f of x and f of a can be made less than epsilon, where epsilon is any positive real number, as long as x and a are close enough. Okay, so that's the hint for the proof, and you should try the rest. So here in this theorem, the important assumption is this uniform convergence. So if this sequence converges uniformly to this function, then the continuity of each of these terms in the sequence is inherited to the limiting function. Okay, if this convergence is not uniform, then we may have a trouble. Let's see an example. All right, consider this sequence of functions. So that is, for each natural number n, we define fn of x as equal to 0 if x is negative or 0, or equal to nx if x is greater than 0 and less than 1 over n, and equal to 1 if x is greater than or equal to 1 over n. And this function looks like this. If n is equal to 1, then it looks like it's 0 in the negative side up to x equal to 0, and it increases linearly to 1, then stays 1. Okay, so that's 1 and that's 1. This is f1 of x. And f2 of x is similar, but it will increase to 1 by when x equal to 1/2. Okay, so this is f2 of x. And obviously these functions are all continuous functions, right? Now, if we increase n to infinity, then the limiting function becomes this. That is 0 if x is less than or equal to 0, and 1 if x is strictly positive. And obviously, this function is not continuous. So this function looks like this. It's 0 up to this point and 1 all of a sudden at this point. So in this case, the continuity of each term of this sequence of functions is not inherited to the limiting function. In fact, this convergence is not uniform convergence, but only pointwise convergence. Let's visualize how this function sequence of functions converges. So we have something like when n is equal to 1, we have something like this. So let's pick a somewhere between 0 and 1. Okay, so this is a. So when n is equal to 1, the value is here. When n is equal to 2, the value becomes maybe 1. Okay, so if the value of a is somewhere here, then when n is equal to 1, that's this. And when n is equal to 2, that's this. When n is equal to 3, maybe here. And at some point, it becomes 1. It converges to 1. Okay. But depending on where we take this a, the number of steps required to converge to 1 is different. So it's roughly, very rough sketch, but it's roughly speaking, this is not converging to 1 uniformly, but it depends on where we are here. So in this case, the continuity of each function is not inherited in the limiting function. Uniform convergence implies more nice properties. And when we studied the calculus of power series, we had something like this. Suppose f of x or f of t is a function defined by a power series, then the integral of that power series can be calculated from the partial sum. Okay, so fn of t is the partial sum up to the nth term of the power series. And we first calculate the integral of the partial sum and then take the limit. So in other words, we could, so this f of x is just limit of the partial sum. So we could swap the order of integral and limit in the case of power series. And more generally, if a sequence of functions, so not necessarily partial sum of power series, so any sequence of functions, if it converges uniformly to some function, then we can do the same thing here. So in other words, we can swap the order of integration and limit. So let's formally state this fact. Actually, this limiting is limit is uniform convergence. Okay, so maybe we should put unif here. So that means if fn converges uniformly to f function f, then the integral of this uniformly converges to the integral of this. Okay, so suppose a sequence of functions uniformly converges to f of x, and let f of x be the integral of this function, and fn of x be the integral of fn. Then maybe it may not be 0. Let's say a here. Of course, x and a are in the interval where these functions are defined. And then the new sequence of functions, these primitive functions, converges uniformly to this function. By the way, we are assuming some interval I in all of this, so this is also on I. Okay, so let's prove this. Suppose this interval is included in some other, another closed interval between alpha and beta. Okay, so by assumption, this sequence converges uniformly to f of x, so that for any epsilon positive, we have f of x, and for all x, of course, and fn of x can be made less than epsilon over beta minus alpha. So beta minus alpha comes from here. And therefore, for any x in the interval, we have f of x minus fn of x. Absolute value is less than or equal to ft. So this is the triangle inequality. And this is less than this, so we have epsilon beta minus alpha dt, which is let's see, which is this is actually equal. So epsilon x minus a beta minus alpha, and beta minus alpha is greater than any of these, right? Because this interval includes this interval, and both x and a are within this interval I, so this part is less than 1. So this is less than epsilon. So that means irrespective of x, this holds. Therefore, this sequence, capital F or Fn, converges uniformly to this function, capital F of x. We are done. And a similar argument applies to differentiation, of course. So if Fn, assuming all these are differentiable, uniformly converges to f of x, then the derivative of fn also converges uniformly to the derivative of f. And this can be proved in a similar manner as we did for the power series, so we'll skip it. If you want the details, you can have a look at the lecture notes. So that's all for this video. See you later.